Ever wondered how your internet data finds its way to you? Imagine sending a letter to a friend in another city. You drop it in the mailbox, and somehow it arrives at their doorstep days later. In the digital world, routing plays the postman's role, but at an incredibly faster pace. Routing in computer networks is the sophisticated process of directing data packets from their source to their destination across multiple network nodes. Here's how it works. Each piece of data, whether it's an email, a web page, or a video stream, is broken down into smaller packets. These packets travel through various devices called routers, which act like traffic directors on the internet highway. The routers examine each packet and decide the best path it should take to reach its destination quickly and safely. This journey is crucial because it ensures that the information you send and receive over the internet is not just fast, but also secure and reliable. Routing is the backbone of internet connectivity, affecting everything from your video call quality to how swiftly your online games respond. Let's dive deeper into how routing actually works and what makes it so crucial for your daily internet usage. The brain behind the operation, routing algorithms. When data needs to travel across a network, it doesn't just randomly bounce from one point to another. Rather, it's guided by a set of sophisticated rules and calculations collectively known as routing algorithms. These algorithms are the maestros conducting the symphony of data traffic, ensuring each packet reaches its destination via the best possible route. To understand how these algorithms work, imagine you're trying to find the quickest route to a friend's house. You might consider factors like the number of traffic lights, the usual congestion on different roads, or whether some streets are closed for repairs. Routing algorithms do something similar, but in a much more complex environment. They evaluate multiple metrics to determine the optimal path for data packets. These metrics include hop count, which is the number of steps or nodes a packet passes through, bandwidth, indicating the maximum rate of data transfer along the links, and delay, which measures the time it takes for a packet to reach its destination. Among the most renowned routing algorithms are Dijkstra's and Bellman-Ford. Dijkstra's algorithm, a real crowd pleaser, is known for its efficiency in finding the shortest path between nodes in a graph. It updates its knowledge of the shortest path with each node it processes, making it particularly useful for networks where cost metrics are constantly changing. On the other hand, Bellman-Ford is like the sturdy, reliable workhorse of routing algorithms. It's especially useful in networks where there might be negative costs, as it can handle these complexities. Bellman-Ford works by iteratively relaxing the costs of the edges, adjusting estimates of the shortest path until no further improvements can be made. These algorithms, by analyzing various metrics, enable routers not just to select a path, but to choose the most efficient one based on current network conditions and the data's specific needs. With these algorithms, routers can decide the most efficient path for data, but how do they keep track of these paths? Imagine having a map that updates itself. That's what routing tables do. These tables are fundamental tools within routers, acting much like a constantly evolving atlas of the internet. They hold crucial data about which paths to take to ensure information packets reach their destination efficiently. Let's delve a bit deeper. A routing table in a router stores the routes to various network destinations. It's not just a static list, it adapts as the network changes. Each entry in the routing table typically includes the destination network, the next hop towards that destination, and other route metrics that influence path selection, such as distance or cost. Think of the next hop as a guidepost on the road. It tells the data packet where to go next on its journey across the network. This is vital because each packet might traverse multiple routers before reaching its endpoint. The next hop information ensures that each router knows exactly where to send the packet next, without needing to understand the entire path from start to finish. Routing tables are dynamically updated through interactions with routing protocols. These updates occur whenever there's a change in the network, such as a new router being added, a router going offline, or even changes in traffic conditions. This dynamism allows the network to be resilient and efficient, adjusting routes based on current conditions to optimize data delivery. These tables are essential, but they need constant updates. This is where routing protocols come into play. Not all routes are set in stone. In the world of network routing, decisions can be made through either static or dynamic routing, each serving distinct purposes and environments. Static routing is the manual configuration of network routes. Network administrators explicitly define the paths that data should travel between devices. This method is straightforward and doesn't require the exchange of routing information between routers, which reduces the bandwidth used for routing data. It's particularly useful in smaller or more stable networks where changes are infrequent and predictability is key. For instance, in a network connecting a limited number of devices that do not often change, static routing can provide a simple, low-overhead solution. On the flip side, dynamic routing is like the adaptable, quick-thinking member of the routing family. It uses protocols to automatically adjust to changes in the network. This type of routing is essential in larger, more complex networks where network topologies change regularly. Dynamic routing protocols respond in real time to network changes, such as failed links or congested routes, by finding new paths for data. This adaptability makes dynamic routing invaluable for ensuring consistent network availability and performance. Dynamic routing's ability to scale and adapt makes it ideal for the Internet, which is a vast network of continually changing paths and connections. It supports the growth and the dynamic nature of modern network environments, ensuring that no matter how or where the network shifts, connectivity remains intact. Dynamic routing adapts to network changes. But how do routers communicate these changes? Routers need to talk, and routing protocols are their language. Imagine a bustling city where each street intersection has a traffic controller, directing vehicles efficiently to their destinations. In the world of networks, routers act as these controllers, and routing protocols are the rules and signals they follow. Let's start with the basics. Routing Information Protocol, or RIP, is one of the oldest protocols still in use. It's like an old town crier passing messages from one router to the next, using hop count as its primary metric. However, due to its simplicity and limitation of only counting up to 15 hops, it's more suited to smaller networks. Next, we explore the Open Shortest Path First, or OSPF. This protocol is like the postal service of network routing, delivering data packets based on the shortest path available. It's more sophisticated than RIP and can scale to larger and more complex networks. OSPF is classified as an Interior Gateway Protocol, or IGP, which means it operates within a single autonomous system. On the grander scale, we have the Border Gateway Protocol, or BGP, the backbone of the Internet. BGP is an Exterior Gateway Protocol, or EGP, which means it's used to manage how packets are routed between different autonomous systems. It's like an international diplomat negotiating paths across countries, ensuring data can travel globally. Interior Gateway Protocols like OSPF and Enhanced Interior Gateway Routing Protocol, or EGRP, focus on routing within a single network or organization. They ensure that all routers on the internal network are in sync with each other. Exterior Gateway Protocols like BGP focus on external data traffic, managing information between distinct networks, ensuring they can communicate effectively. These protocols dynamically update their routing tables based on the information received from neighboring routers. This dynamic conversation between routers allows the network to adapt to changes, maintain connectivity, and route data packets efficiently. Effective communication between routers ensures smooth data transfer. But what happens when there's a change in the network? Change is constant in networks, and routing convergence is key to adaptation. Imagine a bustling city where roads constantly shift and change. In the world of computer networks, routing convergence is much like updating maps in real time to reflect those changes, ensuring that data packets always find the quickest and most efficient routes to their destinations. Routing convergence refers to the process by which routers come to agree on the best paths for data following changes in the network. This could be due to added routers, changed policies, or failed links. When a network change occurs, routers communicate with each other, using protocols like OSPF or BGP to update their routing tables. This synchronization helps prevent data loss and minimizes delay in data delivery. However, the speed of convergence is crucial. Slow convergence can lead to routing loops or prolonged periods of downtime, severely impacting network performance. Fast convergence, on the other hand, helps maintain a resilient and responsive network environment. Routing convergence keeps the network stable and efficient, ensuring that no matter the change, your data finds its way. We've traveled through the complex world of network routing. Let's take a moment to recap what we've discovered about this crucial process. Firstly, routing algorithms stand as the backbone of network routing, meticulously calculating the best paths for data to travel. These algorithms weigh factors like bandwidth and delay to ensure that each packet's journey is as efficient as possible. Next, we delved into routing tables, which are essential tools for every router. These tables hold the roadmap for packets, detailing known networks and the next steps to reach them. They are dynamically updated to adapt to the ever-changing landscape of the network. We also explored the dynamic interplay of routing protocols, which help routers communicate and update their routing tables. These protocols, whether they're for managing routes within a single domain or across multiple domains, ensure that our data finds its way efficiently. Lastly, we discussed routing convergence, the critical process that helps maintain consistent and reliable network communication following any changes in the network topology. Understanding these elements of routing helps us appreciate just how our data packets navigate the vast network to reach us. Next time you stream a video or send an email, remember the intricate dance of routing that makes it all possible.